Hi everyone and welcome back to PrepFusion. I am Anish and today we will start with the lecture 43 of our electrical machines chapter. Right? Today we will discuss about the torque, sleep characteristics and testing of induction motor. Okay. So what is torque sleep characteristics? Right? That we want to understand. So before understanding that, basically it means I want to plot my torque, right, as a function of slip. Okay, let me change the color. I want to plot my torque as a function of slip in a graph, right? That is what it means, torque slip characteristics. So as my slip changes, how does the torque changes, right? That is what I want to plot. So for that I will need a expression for torque, right? So this is the circuit. If I write this resistance totally here, I don't write the like that fictitious resistance and the rotor resistance separately. I write them together. It is R2 by S jx2 dash. Okay. So I want to make few approximations. So like here, right, for finding out the this torque expressions, we have to make few approximations. The first approximation that we will make is that we will assume that the stator, okay, let me change the color, stator drop is very low. We'll assume that the stator drop is very low. Okay, that is what we will assume. So here if stator drop is very low, we can approximate our circuit just like transformer. I will shift the stator resistance and the stator leakage reactance to the other side. That will be helpful for me. How it will be useful, I will explain just in a second. Okay, so this is the first approximation that I will do. Okay, because I will assume that the stator drop is very low. Okay, so can you tell me what is the air gap power? What is the air gap power? If you remember, the air gap power can also be written, right, Pg is equals to 3 into I2 R whole square into R2 dash divided by S, right? This is what my air gap power is. This is what my air gap power is, correct? So the important fact to matter here is what is my mechanical developed power? Mechanical developed power is basically Pg minus the rotor copper loss. Rotor copper loss, right? This is the mechanical power minus the friction and windage loss. So what I will do, I will neglect this rotor copper loss. I will neglect the friction and windage loss. So then my Pg and Pe mechanical will be same. Then basically the torque expression comes out approximately. I'm doing few approximations just for our simplification. Okay, so approximately the torque developed torque or the air gap torque, right, approximately comes out to be this air gap power Pg divided by omega into r, because rotor is rotating with a speed of omega into r. And what is Pg? Pg is equals to 3 into I2 dash r, I2 dash into whole square into r2 yeah, into r2 dash divided by s, basically, right, divided by omega r, whatever is the omega r value, right? So what is omega r basically? Like, as I know, like I know this value, right? S is equals to ns minus nr by ns. Can I write this also, that s will be equals to omega s minus omega r divided by omega s. Okay, so this is my slip. Okay, so I can say that from here I can write what is omega r equals to. Omega r is equals to basically 1 minus s into omega s, right? That is what my omega r is equals to. Okay, this is one of the relationship. Now let us discuss what is I2 dash. So I2 dash from this circuit, right? Will I be able to find out I2 dash? So let's assume that I'm applying a voltage V1, okay, or V, whatever you want to say, V1. I'm applying a voltage V1. What will be I2 dash? So I2 dash will be equals to I2 dash will be V1. Remember, V1 is the phase voltage. Okay, if they give you the line voltage, you have to convert it into phase. So V1 is the phase voltage. Okay, V1 is the phase voltage. So I2 will be this V1 divided by this whole impedance, right? Whatever is this impedance. So reactance is also gone there. So it is x1 plus x2 dash. So this will be under root R1 plus R2 dash divided by S plus x1 plus x2 dash whole square, right? Okay, this is what my I2 is equals to. So what will be basically my uh, what do you call this value, right? So okay, actually what they are doing, they are not doing this approximation. So roughly, right, at full load, one more approximation, last approximation. Okay, last approximation at full load, I will assume that omega r is roughly almost equals to omega s. Basically the slip is roughly almost zero. Like at full load, you know, right, full load speed of an induction machine, like if you have heard, like it is rotating at 1440 rpm and ns is 1500 rpm. So it is very near. So we will do this approximation, one more approximation, okay, for our simplification. So basically what I can write, this developed torque, right, will be equals to pg. Pg is 3I2 whole square r2 by s divided by omega r. So this will become 3 by omega s, which is a constant number basically, into I2 whole square divided by R2. So R2 dash will be there. I2 whole square is V1 whole square divided by R1 R2 dash x1 plus x2 dash whole square. Okay, and this, right, will be R2 dash divided by s. So basically we will try to approximate it in like we will try to divide it in two regions. One will be the low slip region and one will be the high slip region. Why? I will explain just in a second. So this is my slip formula, right? Slip is what? Slip is ns minus nr divided by ns. Okay, which is also equals to omega s minus omega r divided by omega s. Okay, now first of all we will try to see what is the torque slip characteristics in low slip region, right? So in low slip region, Low slip region basically means my S is very less than 1. That is what low slip region means. It is nearly, S is nearly equals to 0. Okay. So if I see here, right, if it is low slip region, this two quantities are getting added and I am dividing by S. So let me take few numbers here. Okay. So let's assume that both R1 and R2 dash are 1 ohms. So it is 1 plus 1. Now let's assume that the slip is 0.04, right? So what is the value here? So it will be 1 by 25, so it will be 26 ohms, correct? Now let's assume I change the R2 dash. So let's I keep the R1 same, I change the R2 dash to 2. What is the value here? It becomes now 51 ohms, right? And in the third case, if I change the R1 now, if I change, make the R1 to be 2 and R2 dash is same, what is the value? It is 27 ohms. So are you able to observe something? So there is huge delta here, right? But here is less delta here, right? Why? Because like if I change my R1, it does not make much of a difference in the final result. But if I change R2, it makes a final difference, right? So basically here R2 dash by S is a dominating quantity. R2 dash by S is a dominating quantity. So roughly out of all this, like x1, x2 also will be very low values, right? So basically what do I mean by this is my R2 dash divided by S will be greater than, very larger than x1 plus x2 whole square, x2 dash whole square, and my R2 dash by S will be very larger than R1. So I can neglect all this in low slip region. I can ignore all this. I will not ignore here, right? Because here nothing is getting added, right? Only this one is present. I will not ignore this. Okay. So roughly in the low slip region, the developed torque comes out to be what? The developed torque comes out to be 3 by omega S into V1 whole square into R2 dash divided by S divided by this R2 dash divided by S whole square, right? So I will just add few pages. So it roughly comes out, this 3 by omega S is a constant, right? Roughly, okay. Roughly comes out V1 whole square divided by R2 dash into S, okay. So roughly I can say in low slip region, what is happening is that my developed torque is basically proportional to the slip. If slip increases, developed torque also increases. Okay, it is almost like a linear relationship, right? Now what happens in a in a high slip region? What happens in a high slip region? So in high slip region, what happens? So case 2, high slip region. So in high slip region, basically my slip is approximately roughly equals to 1. If it is roughly equals to 1, right, what is my torque value equals to? So torque value, right, because here it is roughly like something is getting added up here, R1 plus R2 dash divided by S, as it is roughly equals to 1, right, I can simply ignore it because things are getting added up here. So that's why I can simply ignore the S because it is roughly almost equals to 1. I will not ignore here because here, right, there is no addition or like the addition subtraction, no quantity is getting added or subtracted, right? So this will remain here, but here I will roughly make it equals to 1. So this will be R1 plus R2 dash whole square. So my developed torque is 3 by omega S, and it is V1 whole square divided by R2 by S. This will be r2 dash by s, this will be there, divided by the bottom will be almost constant, r1 plus r2 dash whole square plus x1 plus x2 dash whole square, right? So basically what is happening this time, right, this time what I can observe, that the developed torque is proportional to 1 by s. So it is just like, it will just be a what, rectangular hyperbola, okay, it will just be a rectangular hyperbola, right? So roughly the graph will look somewhat like this. This text will change actually, this will be here, this will be linear, this will stay here, this will be here, yeah. So initially it is linear. So initially if the slip is increasing, this is with respect to rotor speed, and rotor speed is like kind of proportional to the slip only. Okay, this is with respect to rotor speed. If rotor speed increases, the slip okay, sorry, okay, one mistake, no, this is correct only, this is correct only, okay. We are plotting with respect to rotor speed now, okay. So like here what we can do, what will be the graph for the slip? So for the slip, right, if rotor speed is 0, if nr is 0, what is the value of slip? If nr is 0, the value of the slip is what? The value of the slip is 1, correct? So here the slip is 1, highest slip region, slip is near about 1, okay. And if let's say this is the like low slip region, why low slip region? Because this is the case where the rotor speed is very high, so nr is very high, right? If nr is very high, that means what? Nr is very high, that means what is s? S is ns minus nr divided by ns. So if nr is increasing, what does that mean? That means that slip will reduce. So this is the region, low speed region. So at rated condition, where almost my nr will be equals to ns, there will not be any torque developed, right? Because there will not be any current. So that this point is what? This point is basically ns, right? My rotor speed is equals to ns. That's why the torque developed here is 0, right? That's why the torque developed here will be 0, because there will not be any currents in the rotor, because there will not be any flux cut, because rotor will rotate in the same speed of the magnetic field, so no flux cut will be there. So this is the point where my slip is what? So this is my slip. Slip is equals to 1. Here my slip is equals to 0. Okay. So basically in the low slip region, what it is linear. And remember, I'm going in this direction for slip, right? I'm going in this direction. So if I'm moving in this direction, so the graph will be a bit different actually, that is the problem. So if it is linear, right, if I'm moving in this direction, so here if slip is increasing, if I go from right to left, so as in the, so this is the region, so basically I have divided my regions. So this is the low slip region, low slip region, okay. And this, let's assume this portion is the high slip region. Okay. So what can I say? That if I'm moving in the left, like in this region, if I see, so in the low slip region, what we have concluded in the low slip region, we have concluded that basically my developed torque is proportional to the slip, directly proportional. So if I'm moving in the increasing direction, so torque also will increase. So I'm observing torque here is increasing, right? Linear. So here it is linear. In this region, right, it is rectangular hyperbola. in the high slip region. Sorry, this is the low slip region. In the high slip region, I observe that it is inversely proportional. It is just like a rectangular hyperbola. That is, it is, if the slip increases, torque will reduce. So if I notice in this region, right, I'm moving, the slip is increasing, going from right to left, the slip should increase, but torque is reducing. Okay, that's why this is called as the high slip region. Okay, and in between there will be some maxima, and then this will follow basically. So I hope you have understood this low slip high slip thing. Okay, so in between also roughly I cannot comment what will be the characteristics. Roughly it will be some characteristics. Okay, roughly it will start to reduce only. Okay, with increasing rotor speed. So we have plotted with respect to rotor speed as well with respect to slip, because both are saying the same thing but in opposite manner. Because slip, if I go from left to right, slip reduces but rotor speed increases. Okay, I hope this point is clear. Now we will derive the expression for starting and maximum torque. Okay, so first let's derive the expression for starting torque. Okay, so the first expression is the starting torque. Okay, this is the first expression, that is the starting torque. So what is the starting torque? Basically starting what happens, starting nr is 0. If nr is 0, what is the slip is simply 1, right? So the starting torque will be very simple, right? I will just put on the developed torque expression. This is my developed torque expression, right, that I derived here. I'll just put here s equal to 1. So T starting will be equals to 3 by omega s V1 whole square into R2 dash divided by R1 plus R2 dash whole square plus x1 plus x2 dash whole square. Okay, so this is the expression for starting torque. Now let's derive the expression, the slip at which maximum torque will happen, and the expression for maximum torque. So we will now derive the expression for maximum torque. So this is the expression for maximum torque, and the slip at maximum torque is, let's assume it is Sm, right? Okay, so what is the torque expression? Torque expression is this, right? This. So with respect to slip, we have to find it out. So what we have to do, we have to take the derivative with respect to slip, right, and make it 0. That will give me the expression for maximum torque. Okay, so for our simplification purpose, what am I doing is I'm writing x1 plus x2 dash equals to x, because it is just a constant number, right, for our simplification. Okay, so if I differentiate, this 3 by omega s is a constant number, so basically dt upon ds is equals to omega s. V1 also is a constant, R2 dash also is a constant, just s is a not a constant, right? So 1 by s, if I, okay, if I, can I bring this s in the bottom? uh, can I take it in the bottom? No, let's not take it in the bottom. Or I can take it in the bottom, right? Yeah, that's not a problem actually. Yeah, that's not a problem. So this will be basically can this, oh, this is 1 by s. So it is like a chain rule, right? I can use a chain rule as well. So I can write, can I use a chain rule? I'm just thinking what is the easiest way. Okay, so what I can do, right? This is a product of two functions, 1 by s and whatever is in the numerator here, right? So this 1 by s and whatever is in the numerator. So I will differentiate this one first. So this will be minus 1 by s whole square into whatever is in the numerator, that will stay here. So I'll copy this and paste this over here. Okay, then plus what I can write is, I can write here uh, I can write here the now I will differentiate this one. If I differentiate this, right, it's simply minus of this whole square, right, numerator whole square. So this I can copy, this will be whole squared multiplied by the differentiation of the inside function. Correct, I'm running out of space, I'm sorry. Okay, so I'm running out of space over here, multiplied by the this differentiation of the inside function. So this will be basically minus of r2 dash divided by s square. Okay, oh, also 2 is there, right? Okay, into 2 into, sorry, okay, I cannot, okay, it's complicated, it's quite complicated. Okay, so basically, right, shall I do it? Okay, I should have, maybe I should have chosen something else. Okay, it's fine, we have gone ahead with this, I will do this only. So this will be basically what, this will be 2 into r1 plus r2 dash divided by s into minus of 1 by s square. Okay, no, sorry, not minus of 1 by s square, what am I doing, minus of r2 dash divided by s square. Okay, into, of course, this term will still be there, 1 by s will still be there, right, this 1 by s. I'm just applying chain rule, like you can do your differentiation with your own methods, no problem. So basically, right, this will be cancelled. Okay, one of them will be cancelled. So, and 1 by s also will be cancelled, right? So this will be minus 1 by s will stay here, plus this will be 2 into, okay, s square is also there. Okay, 1 by s also will be cancelled, basically s square also is cancelled. This is 2 divided by s into r2 dash, okay, into r1 plus r2 dash divided by s. Okay, this also divided by this, like, numerator, right? Paste this over here, this should be equals to 0. Okay, so what can I do, what things can I do, that is what I'm trying to figure out. So there will be some cancellations here, right? So this will go on that side, so basically this will be my sm, right, sm. So this will be sm into r1 plus divided by sm whole square plus x1 divided by x2 dash whole square plus 2r2 dash into r1 plus r2 dash divided by sm. Okay, so can I do anything? Can I do any simplifications, further simplifications? Okay, sorry, this is already x, right? Why am I writing this? This is already x square. Why am I making my life more uncomfortable? Okay. Okay, so what else can I do? This is equals to this, right? So basically, okay, so sm into r1, okay, it is 2 into r2, this, right? 2 into r2 r1. Okay, if I square this, so this is sm into r1 whole square plus r2 dash divided by sm whole square plus 2 r1 r2 divided by sm plus x whole square equals to 2 r2 dash divided by r1 plus r2 divided by sm. So what am I observing is sm into r1 whole square plus r2 dash divided by sm whole square, this will be whole square, plus 2 r1 r2 dash, okay, plus sm x whole square. This will be basically 2 r1 r2 dash plus r2 whole square, r2 dash whole square divided by sm, right? So what is happening is, if you see, 2 r1 r2 dash is getting cancelled, r2 dash, okay, this will be whole square, right? This will be whole square, r2 dash by sm, I can take it on the other side, okay, and this sm I can take common. So sm, if I take common out of this, right, it is r1 whole square plus x whole square equals to r2 whole square divided by sm. So from here I can find out the value of maximum slip, right? Sm whole square. Sm whole square comes out to be basically r2 dash whole square divided by r1 whole square plus x square, or my maximum slip, right? Sm, it comes out to be r2 dash divided by under root r1 whole square plus x square, okay. So this is basically the maximum slip. This is the condition for, sorry, this is the condition for maximum torque, slip at maximum torque. From here you will be able to find out nr, right? You will be able to find out nr, correct? Nr max will be what? Nr max will be 1 minus sm into ns. Okay, now let me write the maximum torque Tm. So what is the developed torque? Developed torque is this, right? It is this. So one thing I can replace over here, what I can replace is that I know that this, right? I know this equation, r2 dash whole square divided by sm is this value, okay. So can I, somewhere I can use it, or okay, one more thing I can do, I can do this, that r2 dash divided by sm, right? Okay, okay. So basically you can put the value of the maximum torque over here, you can put it here, over here, something, some weird like random value will come out, okay. So yeah, I can put it over here if you want to. So just put here, just put the maximum slip value and you will get the maximum torque, okay. I can derive it for you, but it's like you don't need to remember, just remember this much is enough, okay. So I also do tend to forget this value, okay, but if for some guys, some expert guys who want to remember this, right, they can remember it. So the maximum torque comes out to be, remember this is the equation, right? So what I can do is I can write r1 square plus x whole square is equals to, I can take the sm on that side, r2 whole square divided by sm whole square. So I can take under root on both sides. So here what I can say is r2 dash divided by sm will be equals to r1 square plus x square whole under root. Okay, so that is what I will do. I will replace this r2 dash divided by sm with this value. Okay, so this will be 3 by omega s, this will be v1 square, this will be replaced with this value r1 whole square plus x whole square whole under root. Okay, what about the other portion? What about the denominator? So denominator, this will be r1 whole square plus r2 divided by s whole square is this whole square, right? It is simply equals to r1 whole square plus x square plus this is also x square, correct? So what do I get over here? This basically comes out to be 3 divided by 2 omega s v1 whole square into r1 whole square plus x whole square whole under root divided by r1 whole square plus x whole square. Okay, so this is what I get. Okay, so now I can just take the, like I can divide these things, right? I can simply divide these things. So this will be basically 3 by 2 omega s v1 whole square divided by r1 whole square plus x whole square whole under root. Okay, so this will be the basically the torque expression. Okay, this is the maximum torque expression. If someone wants to remember, they can, but I will not recommend it. I will tell you the next relationship that is very important, that you can remember, that will be very very handy for you. Okay, that you can remember, that will be very very handy for you. Okay, okay, like few people what they do is they neglect the stator, resistance. Okay, so basically if we neglect stator resistance, so basically what will be the maximum slip, what will be the value of the maximum slip? So sm, right, is equals to what? Sm is equals to basically r2 dash divided by under root r1 whole square plus rx whole square. So basically approximately the slip comes out to be r2 dash divided by x. Okay, this is what my approximate slip comes out. So approximately my maximum torque then will come out to be basically, so r2 dash by sm will come out to be x. So if I'll neglect this, right, this will be 2xm basically. So basically r1 will be neglected. So basically torque will be 3 by 2 omega s into v1 square divided by x. Okay, this will be the basically the torque. Okay, so and x, right, again if I neglect the totally neglect the stator impedance, I mean stator impedance, if I neglect, right, impedance, I know basically my, like then what will happen, that means what, if I neglect the totally the stator impedance, that means like overall like r2 dash will be very very higher than r1, that is the first thing. Next thing is x1 plus x2 will roughly be equals to x2 dash only. Okay, so this is what my x2 dash, this is roughly will be equals to x2 dash only. So this is another expression that they do, but this is not that important. The important factor is the relationship between the starting torque and the maximum torque. Okay, so here I have starting torque, where did it go? So this is known as the starting torque when the rotor speed is 0, and this is the maximum torque. So I will find out the ratio between the starting torque and the maximum torque. So it is basically T starting T maximum. So what is the expression for T starting? T starting was this value, right? We had, yeah, this value. What is T maximum? T maximum is this value without any approximation. Something is wrong, huh? Something is wrong. Did I forget to put any under root or something, huh? Okay, R2. Okay, R2 is still here, right? Okay, no, it is correct only. It is correct only. Here there is no R2, right? Okay, so things will cancel out. So basically this will V1 square will cancel out, omega s will cancel out. This will be 2 will still be there. This will be R1 square plus x square whole under root divided by R1. Okay, R2 dash also will be there, R1 plus R2 dash whole square plus x whole square. Okay, so I want to write this in terms of maximum slip. So I know what is my, like, this expression I know, right? I will copy this expression, this one. So I will replace this, right, with R2 dash divided by SM, right? And what is R1 plus R2 whole square? Okay, R1 plus R2 whole square, I don't know what it is. Okay, okay, let me just replace this first. So if I replace this, right, so basically the ratio between T starting and T maximum here comes out, this is equals to R2 dash divided by SM into R2 dash, 2 is obviously there, divided by R1 plus R2 dash whole square. Okay, R1 plus R2 dash whole square. Okay, plus x square. Okay, so what is R1 plus R2 whole square? Do I know any relation here? R1 plus R2. Okay, this is R2 dash. Okay, let me do one thing. This is R1. Okay, let me just anyways, R1 square plus R2 dash whole square plus 2 into R1 R2 dash plus x square. Okay, so now what I'll do is I will try to simply okay, divide by the this value R2 dash whole square. If I try to divide by R2 dash whole square, what will I get? So if I try to divide with R2 dash whole square, this will be 2 divide by SM. This will be R1 divided by R2 dash whole square plus 1 plus R1 divided by R2 dash plus x divided by R2 dash whole square. Okay, so can I do anything? Yes, I know what is R1 plus x square, right? I can add these two up. So what is R1 plus x square? So this is R1 divided by R2 dash. What is r1 plus x square? R1 plus x square is actually r1 plus x square, r1 square plus x square is basically equals to r2 dash whole square sm square, right? So this I can combine, and one more approximation, again one more small approximation I will do. What is the approximation? That I will assume, again generally this will happen, you will see practically this also happening, that the rotor resistance r2 dash will be much greater than r1 stator resistance. This we have to do. So then what will happen is that if this is much higher, so this will go away, right? This will be 0. So this will be 1, and this whole thing will be r1 plus x1. This whole thing will be simply 1 by sm. So here at the top I have 2 by sm, and in the bottom I have this r2 dash divided by sm whole square, and divided by r2 dash is there. So I'm just combining this number and this number. Okay, so r2 dash whole square is there in the bottom, so this will get cancelled, plus 1 is also there. Okay, so basically the starting torque divided by the maximum torque. Okay, the starting torque divided by the maximum torque, this comes out, right, roughly, very important, this you have to remember, unfortunately. So this will be like, this will be utilized in many places. So if I multiply by sm whole square on both sides, this will be basically, if I multiply by sm on both sides, right, this will be 2 divided by 1 by sm plus sm. Okay, very cute and important relationship that you must remember. Okay, this is very important relationship between the starting torque and the maximum torque. Okay, now how can I define the same for full load torque? How can I define the same for a full load torque? So for full load torque, what will change? Basically all this will be same, just x will change, right? Everything else will be same, just this s will change. And what else here? This will be s square into x. Other than that, mostly things will be same. This will not change much, because I want to find out the ratio between the full load torque and the maximum torque. Okay, if I want to find out the ratio between the full load torque and the maximum torque, so roughly, right, my torque expression, basically the torque expression is this, right? If I what is the torque expression? The torque expression is here, developed torque. Okay, so again I will do few assumptions. Okay, now this was the ratio for the maximum to starting torque ratio. Now I want to find out the ratio between full load torque. So let's assume that in full load the slip is SFL. Okay, and what is the torque in full load? Torque in full load is TFL. Okay, so another approximation is R2 dash is much higher than R1. Okay, so then this will go away, R1 will go away basically. Okay, R2 dash is much higher, R1 will simply go away, right? And slip anyway at full load is very low, so this will anyways be dominating, we know this. So roughly the full load torque comes out to be 3 by omega s into V1 square into R2 dash divided by SFL divided by this will be R2 dash divided by SFL whole square plus x whole square. Okay, so one more thing I will assume, remember this time, right, the full load torque, one mistake I made, x is equals to x1 plus x2 dash, right? X1 plus x2 dash. But remember this thing, that what is my basically x2 dash equals to. So if you remember this thing, if the rotor is rotating with some slip, right, my x2 dash is SFL, whatever is the slip, into the standstill reactance, x2 dash s, right? Okay, whatever, if I want to write here, actually it is equals to x2 dash s, and x2 dash s is SFL into x2. Okay, my eraser is very big. It is SFL into x2. Okay, dash. So my x actually is equals to x1 plus x2 SFL into x2 dash, and what I can approximately write x is approximately equals to SFL into x2 dash, because the frequency has changed, right? Total frequency is SFL into x2, SFL into f. Okay, so this is one more approximation that I forgot to do at that point of time. This will be 3 by omega s v1 whole square r2 dash divided by SFL divided by r2 dash whole square divided by SFL whole square plus SFL whole square into x2 dash whole square. Okay, now what is the starting torque? Sorry, what is the full maximum torque? Expression for maximum torque. So expression for maximum torque is this, right? I will actually take this expression, or no, I will take the rotor resistance, right? That also will be better because r2 dash also cancel out. Where is the maximum? Yeah, this is the maximum torque expression. Okay, anyways, x2 is higher. Yeah, this is fine. If I take this value, right? Okay, sorry, this is something else. Sorry. So this is the maximum torque expression. If I do the division of these two things, okay, I have to write in terms of, sorry, I have to write in terms of slip, right? Sorry. I have to write in terms of slip. So what is the maximum torque in terms of slip? So I know this expression, right? This value I know, r1 plus x2 whole square is r2 divided by sm whole square. So this is whole under root. So whole under root is here. This is r2 divided by sm. So basically this comes out to be 3 by 2 omega s into v1 whole square why is the eraser so big, r2 divided by sm. Okay, so this comes out, so this is my basically maximum torque. Okay, I just want to see how can I cancel out r2. So how can I cancel it out? Okay, this is SFL whole square into x2, right? Anyways, this will be cancelled. Okay, let us see. So 3 by omega s will be cancelled. This will be 2. So basically, right, SFL will be very close to 0. SFL will be very close to 0 because it is full load torque, right? So basically, this will be 0. Actually, this quantity will be 0 only. Does not matter. This quantity will be almost 0. Okay. So if this quantity is almost 0, so if I take the ratio of the full load torque to maximum torque, I get this expression. V1 will get cancelled. This will be 2 r2, this is r2 dash, right? This is r2 dash. So r2 dash will be cancelled. This will be sm upon SFL divided by r2 dash is there. Okay, r2 dash whole square is there, right? Okay, no, r2 dash whole, okay, sorry. If I approximate it, right, this will be what? This will be basically v1 whole square into SFL divided by r2 dash 3 by omega s. And this comes out to be, yeah, so basically if I take the ratio, right, this is the maximum torque expression. So the ratio will be, this will be 2 v1 whole square will get cancelled. This will be SFL divided by sm. Okay, so this will be basically the answer. SFL divided by sm will basically be the answer for this question. I mean, not question, sorry, will be the derived expression. Please remember, please remember that we are doing few approximations over here. Okay, so the approximation is we are very near to the full load. If we are very near to the full load, then the torque expression comes out to be this. I mean the ratio comes out to be this. This also you can remember if you want. Okay, it's okay, you can directly solve using the full equation, right? That is totally fine. Okay, this is one of the expression that you can remember if you want to. Okay, now one more thing is there. This is also known as the stalling torque. Why? So Tm is the maximum torque, right? That the machine can produce. Tm is the maximum torque machine can produce. Okay, so if Tm is the maximum torque machine can produce, it is also called as the stalling torque. Why is it called as a stalling torque? It is called as a stalling torque because what is the balance equation? Balance equation is the developed torque must be equals to the load torque, then it will be balanced. So if I keep on increasing my load torque, the developed torque has to also increase, right? So there is a stall point where my developed torque cannot increase anymore, right? This is the graph, right? Okay, just hold on. Okay, why this is lagging? So this is the graph basically, right? I mean the next page, right? Yeah. So this is the graph. So in this case, if you see, I can increase my torque only up until this point. I cannot go above it. So if my load torque is higher than the maximum torque, then the machine won't start basically. Machine will not run. So basically, let's say you have capacity of eating one biryani, like one plate of biryani. But if I give you 2 plates of biryani, will you be able to eat? No, right? You'll not be able to eat 2 biryani. Even though if you love biryani, you really love. I also love biryani. I miss Kolkata biryani. It's not here in Bangalore. It's not here. So I also love biryani, but you'll not be able to eat it, right? Same here, right? If I keep on increasing the load torque, after a certain point, like after let's say 100 Newton meter, the induction motor cannot develop the torque, right, for balance equation to satisfy. So it will just stall. The machine will not rotate, machine will just stall. So that's why it is also called as the stalling torque. Okay, I hope that is clear. So let's solve few questions on this torque equation, whatever we have learned till now. Okay, so pause the video and try these questions by yourself, and I will come back with the solutions. Okay, this is the third question, and one more question we have. Okay, lots of questions. This question also is there. Okay, so try these questions out and I will come back with the solution. Let's solve this question. A star connected 12.5 kilowatt. Okay, the rating is 12.5 kilowatt, that is the shaft power is 12.5 kilowatt. Line voltage is given to me, V line to line is 208 volts, 60 hertz. Okay, it's 60 hertz, right? Not 50 hertz anymore, so I have to write the frequency. Equivalent circuit parameters per phase. Resistance is given as 0.3 ohms, and the rotor resistance, so this is here. Neglect the shunt branch, right? They have asked us to neglect, so I will directly write here the R1 plus R2, that is 0.5 ohms, and the X1 plus X2, right? The per phase referred quantities X1 plus X2 is 0.41, 0.41, that is 0.82 ohms. Okay, J 0.82 ohms, and we are neglecting this shunt branch, and they are asking the starting current. Starting current will be what? It's very simple, right? I'm applying a voltage over here, that is 208 by root 3, because it is star connected, so it will be 208 divided by root 3, and they are asking me the starting current. Okay, very simple to find out, because remember one thing, right? It is the equivalent circuit parameters. So your load, like actually I should have actually not drawn this at the starting itself, else you will get confused. Actually, right, actually the equivalent resistance is something like this. It is R1 plus R2 dash divided by S. Okay, this will be basically x1 plus x2 dash. Okay, these are the equivalent parameters, correct, if you remember it correctly. So it is short circuited. So basically my current, right, this will be V phase. So current I I starting whatever, like I current will be basically V phase upon whole under root R1 R2 whole square plus x1 plus x2 dash whole square. Okay, so same thing we are doing, because it is starting current, so slip will be 1, so that's why this is coming out to 0.5, this is coming out to 0.82. Now we can very easily find out the values, right? We don't need the frequency because they have given us the reactance directly. If they would have given us the leakage uh, inductance, then we have to use the frequency as well. Okay, so yeah, I guess that is fine. Okay, and one more. Okay. Okay. That is what happens in gate. So here, right, they have told us that the current is 80 volt line to line and the frequency is 320 hertz. Okay, then what will happen? Then what is the starting current? That's why you should read the question. That's why gate questions are very, very tricky if you don't read the complete question. So frequency has one third. So basically, what is my reactance? What does my reactance depends on? So my reactance is proportional to frequency. So the new reactance x2 dash, or basically the new reactance, right, x will be basically what? It will be the f2 divided by f1 into the old reactance, right? So old reactance is this value, right? So it will be just one third basically, because frequency has half. So this is 20 divided by 60. Okay, this will be this is x new, right? X new. So x new will be one third into x old, that is 0.82. So this comes out to be 1 by 3. 1 by 3 is 28. Sorry, 20. Just hold on. This value will be 0.82 divided by 3. 0. 0.2733 ohms. Okay, so now the circuit will be this is not the circuit, right, because I'm not applying 200 volts anymore. I'm not applying 208 volts. I'm applying only 20 volts, right? No, sorry, I'm applying only 80 volts. So the circuit will be, this will be 0.5 ohms. This will not change. R2 will obviously not change. It does not depend on the frequency. This will become J 2.733 ohms. And this will be 80 divided by root 3 plus minus. Okay, so I starting will be equals to 80 divided by root 3, 1 divided by whole under root 0.5 whole square plus 0.2733 whole square whole under root. This will be basically whole squared plus 0.5 whole square whole under root, okay, into root 3 into 80. So it's roughly around 81 amperes. Am I exactly correct over here? Oh, sorry, this is 0.6, right? What am I doing? This is 0.6. Okay. Unfortunately, I don't even know how to add. Okay, I've forgotten how to add. Sorry. That's what happens when you have bad handwriting. Okay, so this is 0.6. This is 0.6. This will be 0.6. Sorry. So 0.6 whole square plus 0.2733 whole square whole under root into root 3, this into 80. So this comes out to be 70.05 amperes. So roughly this comes out to be 70.05 amperes, and this will be your answer, the starting current for this question. Okay, let's now move on to the next one. So next one, so now you will understand how basically our like the wound rotor induction machine is useful, right? Because we can add external rotor resistance. If I add external rotor resistance, the maximum, like the slip at which maximum torque occurs, I can change it. That is the advantage. So what they are telling, I have a 220 volt, 220 volt. This is my line to line voltage, 220 volt, 3 phase 4 pole machine. Okay, 50 hertz induction motor. Wound rotor, right? Wound rotor means I can add external resistance on the rotor side. So wound means provision for addition of external resistance on rotor side. So okay, the stator resistance, magnetic reactance and core loss are totally negligible. So only I have rotor resistance and rotor reactance. Okay, the maximum torque produced by the rotor is 225% of the full load torque. So Tm is 2.25 of the full load torque, which occurs at 15% slip. So Sm is equals to 0.15. Okay, the actual rotor resistance R2 dash is equals to 0.03 ohm per phase. The value of external resistance which must be inserted in a rotor phase if the maximum torque should occur at start. So if I want the maximum torque to occur at start, what needs to happen? During starting, what is the slip? Slip is basically 1, right? During starting, slip during starting is basically 1, right? Because the rotor is just start to rotate, so NR is still 0, right? So basically I want my SM dash to be equals to 1. And what is the slip formula? What is the maximum slip formula? If you remember, it was basically equals to R2 dash upon under root R1 whole square plus X2 dash whole square. So this you have to remember, unfortunately, no other choice. Okay, here if you see, where did it go? Here, right? This you have to remember. R2 dash divided by R1 whole square plus X square. So if you don't remember this, right, this is like you will not be able to solve an exam. So you have to remember this. So this is my maximum slip. So currently what is the, like they have told me to ignore R1 because R1 is not there. So basically my maximum slip roughly comes out to be R2 dash divided by X2 dash. Okay. Currently what is the slip? I know the rotor resistance. From here I can find out the X2 dash because I know the current slip at which maximum torque happens. So it will be equals to Sm is equals to 0.15. Okay, Sm is 0.15, that is equals to R2 dash. R2 dash is 0.03 divided by X2 dash. X2 dash is what I have to find out. So X2 dash will be equals to this 0.03 divided by 0.15. So this will be 0.2 ohms per phase. Okay, so from here I am able to find out. So what I want to do, I want to increase my slip, right? So what I will do, I will just increase my R2 dash. So I will add an external resistance. So my new R2 dash new, right, will be R2 dash plus R external, right? So basically what needs to happen is I want the maximum slip to be 1. So basically R2 dash new by X2 dash should be equals to 1. So basically my R2 dash new should be equals to X2 dash. So which is equals to R2 dash plus R external should be equals to X2 dash, that is 0.2, and R2 dash is 0. R2 dash is how much? 0.03, right? R2 dash is 0.03. So R external will be 0.17. Okay. So this will be the external resistance that I need to add to make the slip occur at starting. Sorry, to get the maximum torque at starting. If I want the maximum torque at starting, I need to add this much amount of resistance. Okay. Let's now solve this. The figure shows the per phase equivalent circuit of a 2-pole 3-phase induction machine. So its number of poles is 2. It's a 3-phase induction machine. Per phase diagram is given. The air gap voltage V0 Vg across the magnetizing inductance is given as 210 RMS. Okay, it is given. This air gap voltage is given 210 RMS. Slip is 0.05. So slip they have given me is 0.05. The torque produced by the motor. What will be the torque produced by the motor? How will I find out the torque produced by the motor? So first of all, what you can do, you don't need to use this formula, right? Whatever we have done, that kind of formula, because here they have directly given you the Vg. So don't use the formula, because that was an approximate formula. If you remember, this is the formula for torque that we derived. I will go back. Yeah, this is the formula, right? Remember, this formula was derived for a certain case. What was the case? We had done few approximations. What kind of approximations? If you remember, this formula was derived for this circuit, so you have to be very, very careful. Okay. Hello. Just hold on. I'll just check. This is fine. Yeah. So the approximation was this, right? This was the approximation here. So just be careful here. You should not always use that formula. If they have given the circuit, then you just see the circuit if you should make the approximation or not. It depends on a lot of things. So here what I can say is this is valid for this circuit, okay, but it is not valid for this question. It is not valid for this question. Okay, so the thing is, because why we did that approximation, because it was very difficult for me to find the Vg voltage, because I wanted to find out the torque developed, right? Vg, that was basically Vg whole square divided by whatever the value, right? It was getting difficult, that's why I had made that approximation. But now it is easy, right? Now they have already given me the Vg voltage. I don't need to do anything. Okay, I don't need to do anything. So I will directly find out the torque. So to find out the torque, first of all I need to find out the air gap power. What will be Pg? Pg will be equals to this 3 per phase, that's why 3 multiplied by the rotor current I2 dash whole square into this R2 dash divided by S. Okay, so what is I2 dash whole square? I2 dash whole square, so this, right, is equals to this R2 dash, and what is the torque developed torque? It will basically be 3 by roughly omega s. You can write omega r as well. Because slip is here, right? Slip is anyways very low, so it's roughly like almost equals to omega s only. So if you want, you can do. If you don't want to approximate, right, you can directly write omega r, but that's fine, I guess. That is not a problem. If you want, you can. So what is omega r? Basically omega r is 1 minus s into omega s. So it is roughly like 0.95 into omega s. So roughly almost equals to omega s itself. So we can make the approximation. So this will be 3 by omega s into I2 whole square. So I2 whole square. So what is I2? I2 is this Vg divided by whole under root R1 divided by R2 dash by S whole square plus x1 divided by x2 whole square. This whole squared, right? This is whole under root into R2 dash divided by S. So from here I know the values. So what is omega s? Omega s will be basically 2 pi ns by 60. So this is 2 pi into ns divided by 60. Or what is omega s? Omega s is basically 2 pi into f, right? That is what omega s is equals to. So it is 2 pi into 50. So it is 100 pi basically, because f is 50. If I am not mistaken, f is given as 50 hertz. Yes. So this will be 3 divided by omega s, that is 100 pi into Vg. Vg is, they have given Vg to be 210 volt RMS. Okay, divided by R1. R1 is given to me. Okay, sorry. sorry. Again, I am doing the same mistake, right? I cannot apply, like, sorry, what am I doing? I2 dash is what? I2 dash is this Vg divided by this impedance. Okay, what am I doing? I'm really sorry. I'm extremely sorry. This will not be any R1 anymore. This will be this, right? Like, I'm just lost in some other thing, right? I'm sorry. So that's why I had explained all these things. Okay, sorry. So this will be this value. This will be whole under root. So it will become much simpler now. So this will be 210 whole squared divided by R2 dash upon S. R2 dash is 0.05 and S is also 0.05. So it basically is 1 whole square plus x2 dash is how much? It is 0.02. So 0.22 whole square. Okay. Into R2 dash by S, which is equals to 1 only. So from here, if I want to write down the values, this will be 0.22 whole square plus 1 into 100 into pi. So this will be 329.365 200 whole square into 3. So this is like 132300 divided by 329.365. So this roughly comes out to be 401.68 Newton meter, and this will be the answer. Okay, so like that's why I was also making the same mistake. Don't make the same mistake. Okay, so yeah, I hope it is clear now, because there is no other way. Like only you can find out the air gap power, because they have not mentioned, like I don't know what is the rotor copper loss. For me to find out the rotor copper loss, I need R2. So rotor copper loss, right? Rotor copper loss, I don't know. Okay, I don't know what is the rotor copper loss. I don't know what is the mechanical, like if I want to find out, still I can, okay, I can know the rotor copper loss actually. Sorry, I can know the rotor copper loss, because rotor copper loss will be what? It will be S times the air gap power. Air gap power I can find out. Yes. Okay. Like here, right? If unless and until it is heavily specified, right, excluding the rotor loss, you will always find out the air gap torque only. Okay, you will always find out the air gap torque only. Even if you like remove the rotor loss, right, I don't feel this will change much, and I think they will give that range. I hope they give that range. Okay, so yeah, let's move on to the next question. So this is the next question. A 3-phase induction motor has a 4-pole star connected stator winding. Okay, so my number of poles is 4. It is star connected. It operates at 50 hertz. Okay, and the line to line voltage is 200 volts. Okay, the rotor resistance per phase is 0.1 ohms. So rotor resistance they have given me per phase is 0.1 ohms. The standstill, very important term, standstill, right? So x to s, right, when slip frequency is 1, sorry, the slip is 1, standstill reactance is given to me as 0.9 ohm per phase. The turns ratio from rotor to stator, so rotor to stator, so nr divided by n stator is 0.67. First time they have given us the turns ratio. So okay, this values, right, then this values whatever they have given us, this is not referred to the stator side. All these values are referred to the rotor side only. So this is not R2 dash, this is not X2 dash. If turns ratio is given, that means you have to understand these values are not referred to the stator side. You have to refer them. Okay. Determine the torque developed at 4% slip. Also the maximum torque the motor can produce. Okay. So the first point, what is the torque developed at a slip of 0.04? If I see 4%, right, 0.04. So for that I have to draw the equivalent circuit. So first of all, they have not given any stator resistance, right? So I can neglect the stator resistance. So basically if I draw the circuit, there will be some parallel branch that will contain the Ri and the Xm. So this will be R2 dash referred to the stator side. I am referring it to the stator side because this voltage, right? This voltage is with respect to the stator. This voltage is not in the rotor side. So this voltage is stator and it is star connected. They have told us it is star connected. So this will be basically 200 divided by root 3. Okay. And this will be basically x2 dash, and it is not standstill anymore because it has, sorry, this will be r2 dash divided by s, right? This will be r2 dash divided by s. This will be x2 dash. Okay. So and then the rotor, we short the rotor, right? Short it. So what is, like, how do I find out the developed torque? For developed torque I have to find out the air gap power. What is Pg? Pg will be 3 into this current, right? Whatever this current is flowing, I2 dash whole square into R2 dash divided by S. So three into R2 dash divided by S. So okay, what is I2 dash then? So how do I, so for that I have to write down R2 dash and stuff. So what is R2 dash? So R2 dash will be the rotor resistance referred to the stator side. So it is basically Ns divided by Nr whole square into the rotor resistance in the rotor side R2. So this will be basically, right, 0.1. So this will be what? This will be basically, this is our 2 by 3, right? So 2 by 3. So this is 3 by 2 whole square into 0.1. Okay. So it is roughly equals to 2.25. Somewhat it will be like that only. 0.67. If I take the inverse, then I do the whole square into 0.1. It is 0.22. 0.223. Okay. So this will be my So 0.3 ohms. This is my R2 dash. Now what is my X2 dash? So X2 dash, same formula will be applied, right? It will be Ns by Nr whole square into X2. Okay, something happened. Okay, so into X2, right? X2 is how much? X2 is 0.9, right? This is 0.9. My handwriting is super bad. So this will be Ns divided by Nr, right? So again it is same, right? Like 1 divided by 0.67 whole square into 0.9. So 0.67 inverse whole square into 0.9. So this is roughly almost 2 ohms. Okay, so this is my X2 and this is my X2 dash and R2 dash. Okay, so I will put it over here. So what will be the, like, basically what is the torque then? What is the developed torque? So the developed torque, T developed, will be basically this Pg upon omega s, right? So because slip is very low again, so it will be 3. What is omega s? Omega s is basically 2 pi f. So 2 pi into f, that is 50. It is 50 hertz, right? It is 50 hertz, yes. 50 into Pg. Pg is this I2 whole square, right? I2 whole square. I2 will be what? I2 will be this voltage divided by the impedance. So this 200 by root 3 divided by the impedance is, just hold on, it is R2 dash by S. So R2 dash is how much? R2 dash we have derived, it is 0.223 divided by S. S is basically 0.04, right? S is 0.04. 0.04 R2 dash whole square, R2 dash by S whole square plus X2 dash. X2 dash is 2 whole square, right? And this will be whole squared basically. So yeah, and this is R2 dash divided by 0.04. Okay, so this value here, right? If I want to compute this value, so okay, this will be hectic. Okay, let me first compute this one. So 0.223 divided by 0.04 whole square plus 4 whole square. Okay, so this is coming out to be 3 by 100 pi into 35.08. Okay, and this is basically 0.223 divided by 0.04. So again this is multiplying by 5.575 and okay 35.08, and whatever this value is, this is 200 whole square divided by 3. So this will be roughly 20.23 Newton meters. That will be the value of the developed torque. That will be the answer. Okay, for the first portion basically. What about the next portion? So the next portion, the slip and the corresponding rotor speed at which the maximum torque occurs. Okay, so the slip and the rotor, okay, slip, what is the slip corresponding uh, to which maximum torque occurs? If you remember the formula for slip, right? Basically how you remember it? So how I, okay, just hold on, give me 1 second. Like how will I remember it, right? How do I remember? So one thing you know, right? One thing you remember, that the rotor reactance was actually equals to S times the standstill reactance. This much I know. So this is how I will remember. I will write here, instead of rotor reactance, I will write R2 dash is equals to SM into X2. and this is how you will remember that Sm is equals to R2 dash divided by x2. And one more thing you will remember, that okay, I remember this, that this was the approximated version. The actual version Sm was actually equals to R2 dash divided by R1 whole square plus x whole square whole under root, right? So like this is the trick basically how you can remember it. Okay, so I'm telling you how to remember the rotor, like the maximum slip formula. Okay, so they're asking us what is the slip and the corresponding rotor speed at which the maximum torque occurs. Okay, so slip will be what, because they have not given us any stator reactance, so it is R2 dash. R2 dash is 0.223 divided by x2. X2 is basically x2 dash, right? This is also referred, actually this is referred, everything is referred, right? So this will be x2 dash is 2, right? So the slip at maximum torque will be 0.223 divided by 2, so it is 0.1115. Okay, that is the slip at maximum torque, 0.1115. Okay, so what we can do is we can, this is the slip, we can this is the one of the answer. What is the other thing that they have asked? They have asked the slip and the corresponding rotor speed. So rotor speed, right, nr will be what? Nr is simply 1 minus sm into ns, right? What is ns? Ns is 120 f by p, so 1 minus 0.1115 into 120 f by p. F is 50, p number of poles is 4. Okay, number of poles is 4. So this is equals to 0.1115 plus 1 into 1500. So this is around 1332.75 rpm. So this is the speed corresponding, sorry, this is nr, right, not ns. So this is the rotor speed corresponding to the maximum slip. Okay, so what I can say now, what they are asking, the mechanical power output of the motor at the condition of maximum torque. Okay, so what is the mechanical power output of the rotor? So what is p mechanical? That is that what they are asking at s equals to sm, right? Very easy to find out. So I can easily find out the air gap power pg. So I know the ratio of pg and p mechanical is what? It is basically, if you remember it correctly, it is 1, like the whole ratio was supposed to be the rotor copper loss is to the mechanical loss. So 1 is to the rotor copper loss is to 1 minus s. Okay, so this will be, basically, so I can say what is my pg? Pg will be 3 into I2 dash into R2 dash divided by Sm, right? Maximum torque. So it is I2 dash whole square basically. So 3, what is I2 dash? Again the same formula, right? Same formula. So this will be V is 200 divided by root 3. So 200 divided by root 3 whole square divided by the, sorry, this, right, divided by the, because there is no stator resistance, only rotor resistance is there, that is 0 point, sorry, it is 0.223, 0.223 divided by the slip, basically 0.223 divided by the slip, maximum slip is 0.115, right? So that is the maximum slip basically. So it is basically 2. So basically in maximum, right, maximum torque, what happens, this equation is followed, right, this equation is followed. So basically r2 dash by sm is equals to x2, so basically this is equals to 2, so this will be 2 whole square plus 2 whole square whole under root whole square into r2 dash by sm, which is basically equals to x2 dash only, that is 2. So this will come out to be, if I find out the values here, so okay, 2 square 2 square 4, 4 plus 4 8, 8 under root 8, 8 is there, and into 2 is there, and into 3 is there, and into 200 whole square divided by 3, so it comes out to be 10,000, right, watts. So this is the air gap power though, this is not exactly the mechanical output power. Mechanical output power will be what? Mechanical output power will basically be, like if I take the ratio of these two things, it will be 1 minus sm into pg, so which is 1 minus sm is 0.1115 into pg, that is 10 kilowatts. So this value will be basically into 1 minus 0.1115, this is 5, it comes out to be 8.85 kilowatts. This will be the answer, okay, to the third portion, right, this is the third portion. Okay, this was the second portion basically. In the second portion we had two answers, one was this was the other answer. Okay, so yeah, that's the solution of this question basically. So we will move on to the next question. So in the next question we have a 3-phase 50 hertz 6-pole induction motor that delivers a shaft output power of 10 kilowatt while running at 930 rpm. Okay, these questions are actually going very lengthy, so let's solve this question. So yeah, this is the last question, and after this we'll not move on to the next topic. Again we have to delay it to the next lecture. Okay, so a 3-phase 50 hertz 6-pole induction motor delivers a shaft output power of 10 kilowatt. Okay, so it delivers a shaft output power of 10 kilowatt. Okay, P shaft is 10 kilowatt, frequency is 50 hertz, number of poles is 6. So remember, this time the synchronous speed will change and the rotor is rotating in 930 rpm. The friction and windage loss account for 1% of the output power. So output power is this shaft power, right? So 1% of this, so friction and windage loss will be basically 0.01 of shaft power. So this will be basically 0.01, so 1 by 100, so 10 into 10 raised to power 3, so yeah, this will be basically 100 watts, because if I multiply here 1 by 100, if I multiply 100, yeah, it is 100 watts. So this is basically the friction and windage loss, and the stator loss, total stator loss, right? Stator loss includes what? Stator loss includes the stator copper loss, right, plus the iron loss. This is what the stator loss includes. Okay, this is equals to basically the 600 watts that is provided. So calculate the rotor input power and the total stator input power. Okay, so what is the rotor input power? Rotor input power is basically the air gap power, that is what they are asking, right? What is the air gap power? So air gap power will be basically equals to the shaft power, output power, plus the friction and windage loss, plus the rotor copper loss. Okay, so do I know the slip? Yes, they have given me the speed, right? Rotor speed. So from rotor speed, I will be able to find out the slip. So what is the slip? So slip S will be ns minus nr divided by ns. So this will be equals to ns is what? Ns this time is some ns is 1000 I guess this time. So ns will be 120 f by p. So this is equals to 120 into f. F is 50 hertz. F is 50 hertz. P is number of poles is 6 this time. It has changed. So it is basically 1000 rpm. So it will be 1000 rpm minus nr is 930 divided by ns. Ns is 1000. So which is equals to basically 0.07. That is what the slip is equals to. Now of course we know this, like this will be so helpful, right? This relation is very helpful. Pg upon P rotor copper loss P mechanical is 1 is to S is to 1 minus S, right? So basically I can write my P rotor copper loss, right, is basically S times Pg. Okay, so I'll replace it because they have asked me to find out the air gap power only, rotor input power. So I don't need the rotor copper loss. I don't need to find it out. I can replace it. So I will replace it. So I can write here that so Pg will be equals to shaft power. I already know shaft power is 10 kilowatts. 10 kilowatts plus the friction and windage loss. Friction and windage is given as 100 watts, right? So it is basically 0.1 kilowatt plus 1 plus S into Pg. So basically Pg into 1 minus S is equals to 10.1 kilowatt. Okay, so Pg is equals to 10.1 divided by 1 minus S. 1 minus S is 1, S is 0.07. So this will be 10.1 divided by 1 minus 0.07. So this comes out to be 10.86 kilowatts. So your air gap power is 10.86 kilowatts. This is the input rotor power. Okay, this is the input rotor power. Now what is the stator input power? So stator input power will basically be, it is basically the input power which is the stator losses plus the air gap power, right? I hope you remember the flow. So the power flow should be in your mind. Okay, so this will be equals to the stator losses is they have provided us, it is 0.6 kilowatt. So this will be 0.6 kilowatt plus 10.86 kilowatt. So this, right, is equals to 11.46. So this is the input to the stator. So this is one of the answer in the first part and this is the other answer, right? Now the second part, this is the first part, right? This was the first part basically. Second part they are asking, calculate the maximum torque. If the maximum torque occurs at 800 rpm, determine the starting torque when the motor is started directly at rated voltage. Okay, so what they are telling me is, if the maximum torque occurs at a speed of 800 rpm. So from here I will be able to get the information about the slip. So maximum torque occurs at 800 rpm. Then the starting torque will be what? What is the starting torque? Okay. So from here I will be able to find out the slip at maximum torque. What is the slip at maximum torque? Slip at maximum torque will basically be equals to ns minus nr divided by ns. Okay. So ns is how much? 1000 minus 800 divided by ns, that is 1000. Okay. So it is basically 0.2. 0.2 is the maximum slip. Now what is the slip equals to? Again, if you remember, slip at maximum torque is simply equals to, like, s into x2 dash is simply equals to r2 dash, if you remember this, right? So from here I will be able to find out the ratio. So basically one thing I know, that I know this air gap power, right? This air gap power I know. This is the power when this is the air gap power when the slip was here, the slip was 0.07. This I know, right? So will I be able to find out the torque at that particular point? So torque is what? Torque is pg upon omega s. That is what my torque is. Okay. So this torque is equals to this value, right? pg is 10.86 kilowatt, 86 kilowatt divided by omega s. Omega s is whatever the value, that is 100 pi, right? So this is my torque basically in the first case, whatever case that was mentioned. For what? For slip. For slip is equal to 0.07. So here, right, I see slip is very low. Slip is very low. So again I can do few approximations. Okay. So what is the actual equation of the torque? If you remember, the actual equation of the torque was basically 3 upon omega s into I2 dash whole square into R2 divided by S. So roughly, what is I2 dash? I2 dash is 3 upon omega s into V square divided by R2 dash whole square divided by S square plus R1 is there, because but they have not mentioned anything about the stator resistance. So stator resistance I will assume, okay, I will assume it to be like, I can neglect it. How can I neglect it? I will tell you, right? R1 whole square plus x square, right? So basically it is low slip region. In low slip what happens? In low slip basically this will be dominating irrespective of the other values, right? So this will be dominating. So what? So I can directly write here, this will be basically 3 upon, that's why you don't need to memorize all those formulas. Without formulas also we can directly derive in the exam hall itself, right? So 3 by omega s into V square divided by R2 dash, so this is not square, sorry, R2 dash basically. So this will be R2 dash into S. Okay. So this is the torque equation. Now what they are asking? They are asking me the torque when the slip is 0.2. This is the slip, right? They are asking me the value of torque at slip, like, sorry, not at this, at starting, right? Okay, they are asking me starting. Okay, what are they asking? They are asking me, okay, maximum torque occurs at this point, determine the starting torque. So how will I determine the starting torque? So again, what kind of approximation we do when slip is very high? If slip is very high, then what kind of approximation we will do? So if slip is very high, right, so I can directly say, if slip is very high, this is the low, like this is the low slip region, because at slip equals to 1, what will happen? This will be basically okay, this, right, this will be converted 3 by omega s into v square divided by r2 dash whole square plus r1 whole square plus x square, right? So this is given to us into basically r2 dash by s, right, which is 1 basically. So again, what other information they have given me this information, right? I know what is my x2 dash. So x2 dash is equals to r2 dash divided by sm. So any other information do I know? Any other information? So okay. So basically, right, I know this torque, right? This is the torque that I have found out. This is the T1, right? Low torque at the low frequency, low slip region, LS, and this is the torque at the high slip region. So this torque is already known to me. So if I take the ratio, and one more thing I will do is I will try to approximate it, right? So approximately, if I assume that the rotor resistance is dominating, then the other values, it will be 3v square divided by r dash 2. That's it, right? So then basically, if I find out the ratio of each s, okay, no. If I assume that the rotor resistance is dominating to this, right? It is not dominating to the stator. So okay, because they have given me this, right? Because one more thing is there. So basically, stator, I can assume my rotor resistance to be dominating than the stator resistance because nothing is mentioned. But here, right, they have mentioned this maximum torque value. So from here I can find out the ratio that rotor resistance is 0.2 times stator, sorry, standstill reactance, correct? So actually it is not much greater than standstill reactance. Standstill reactance is still very high. So standstill reactance is still very high. So what is x equals to? So x is equals to x1 plus x2 dash, right? So roughly I can write it is equals to x2 dash only if I assume that the rotor reactance is much higher because nothing has been mentioned about the stator reactance. So I will assume this, I will do the assumption. So ultimately this value will come out to be r1 dash whole square plus x1 x2 dash whole square. Okay, now this information is known to me, right? This information is known to me, that is r2 dash equals to 0.2 x2 dash. So I can write this over here, that my this is 3 upon omega s v square. Now into r2 is also there, right? Don't mess up the r2 dash. So this will be r2 dash is 0 point, or what is my x2 dash? X2 dash is 5 times r2 dash. So this will become basically 26 r2 dash. Okay, so now if I take out the ratio, basically the starting torque to the torque in the low slip region, right? This will be 3 by omega s will be cancelled, v square will be cancelled, r2 dash will be cancelled. This will be the slip at the low slip at the that particular region, whatever slip we had calculated, and this will be 26 will be there. So 26 yeah, 26 will be in the bottom actually. Yeah, 26 into 1. Okay, so what is the torque here? Torque, have I calculated the torque is this, right? So what is the torque value? So torque value, if I want to find it out, so it is 10.86 into 10 divided by pi, 34.56. okay, so this will be 34.57 basically Newton meter. That is the torque at full load. Okay, or whatever load they have given me. So this will come out to be, so basically my starting torque will come out to be this 34.57 divided by the low slip 0.06 into 26. So actually I am making a huge mistake. What kind of mistake? So this, right, is wrong, whatever I have written, right, 100 pi. Okay, in the previous question also I had made a mistake here, right? That is my mistake here, right? Yeah, this one, this is wrong actually. Why is this wrong? This is not 100 pi, this is wrong, right? It is not 2 pi into f. What is omega s? Okay, I'm really sorry. So omega s is basically 2 pi ns divided by 60, right? What is ns? Ns is what? Ns is the synchronous speed, that is 120 f by pi, 120 f by p. So it depends on the pole as well, right? Because the omega s is the like speed of the rotating magnetic field. If I increase the number of poles, what will happen? So if I increase the number of poles, the omega s reduces. Okay, so it is basically 2 pi into 2 into f divided by p. That is what my omega s actually is equals to. Okay, that is what my omega s is actually equals to. So there I was making a mistake. So basically what will happen, this will be here, right? Another 2 by p factor will come, that's it. Extra 2 by p factor will come, that's it. So this will be like, this will be changed. I will change this. Okay, so basically, right, this is wrong. Just copy this whole thing. So 2 by p factor will come, 2 by p into 2 by p. So 2 p is how many poles we have? It is a 4 pole machine. So this will be divided by 2. So 2 will be multiplied at the top, right? So an extra 2 will be multiplied here, because 2 by, like 2 by p is 4. So it is 1 by, sorry, 2 by 4. So it is 1 by 2. Okay, so this will be multiplied by 2 basically. So this will become 40.46. Okay, so basically 20.23 into 2, so 40.46 Newton meter. Okay, so this is 40.46 Newton meter. So this is the answer actually. Okay, this is the answer for this question. I was really wrong. I am really sorry. Here also the same thing basically, sorry, here also, right? So basically this, right, this torque will be here an additional factor of what, 10.86 into 10 cube divided by 100 pi will be there into 2 ip. That additional factor will be there, and this is a 6 pole machine, right? It's a 6 pole machine, if I remember it correctly. It's a 6 pole machine. So if it's a 6 pole machine, so please don't make this mistake, right? So this will be basically an additional 3 will be multiplied, right? An extra 3 will be multiplied basically. So 34.57 into 3. Okay, so the torque 34.57 into 3, it comes out to be 103 3.71 Newton meter. Okay, so it comes out to be 103.71 Newton meter. So basically what will I write? So now the ratio will be correct. So the starting torque now will be what, 103.71 divided by this, whatever this number is, 0.07 into 26, right? This comes out roughly this 0.07 divided by 26. So it comes out to be 57, something like that, right? So around 57 Newton meter. So without using any, no formula use, right? I have not used any formula. I have derived all the formulas because other educators also will derive it, right? But without using any, like I have not told you any, remember any formula except the maximum slip. That is the most important one. I have just told you remember the formula for maximum slip. That also I have told you how to remember it. Other things, right? You'll do approximation. So do approximations in exam, because you never know what kind of question they will ask, right? So what you should be thorough with, what kind of approximation I should do to the main torque formula, then you will be able to solve these kind of questions, right? So because like there are infinite number of formulas, how many will you remember, right? It is very difficult to remember all these things. So I hope you have enjoyed this. If you have enjoyed this last question, please hit the like button. Please comment down below if you have enjoyed this. So I'll meet you in the next lecture with the remaining portion, that is the dynamic behavior of induction motor, and also we will learn about the stability of induction motor and testing of induction motor. What are the different tests that will happen to induction motor? Thank you for watching, and I will see you in the next lecture. Until then, happy learning.